This video is going to cover a pretty common topic in applications of differentiation, and that topic is optimization. How can we use the principles of derivatives to apply them to kind of real world scenarios where we optimize something? We'll talk about what that means. So a couple of general guidelines for how to approach an optimization question. Number one is we're going to rewrite the scenario as one equation in terms of one variable. So there's going to be a lot of different scenarios we're going to see with optimization questions, and this tends to be, I think, one of the more challenging parts of an optimization question is we take that scenario and we kind of relate it to one single equation in terms of one variable for like a basic optimization question. And then once we do that, we're going to optimize the equation. In other words, we're going to find the maximum and the minimum. And to do that, we take the derivative and set the derivative equal to 0. And then from that we determine whether the critical point or points are maximums or minimums. It's the idea is if we want to find a maximum of some scenario, we take the relative or absolute maximum. If we want to find the minimum, we take the relative or absolute minimum. Okay? So let's go through an example. But the key here is we want to relate this scenario to one equation and set the derivative of that equation equal to 0. Okay, so for example, let's find the dimensions of a rectangle whose perimeter is 100 meters and whose area is as large as possible. So we want to start by setting up an equation where we have a rectangle and we know the perimeter of this rectangle is going to be 100. Okay? So rectangle, we know these sides are going to be the same. Let's call these sides y. And we know the top and the bottom are also going to be the same. So these are x's. And if we know the perimeter is 100 meters, we know that the sum of all the sides here, 2x plus 2y, is equal to 100. And we also know the area of this rectangle is x times y, and the base times the height. So the problem here is the equation we want to optimize, this equation, because we want to find the largest possible area, is in terms of two variables. So what we're going to do is we're going to use this equation to write the second equation down here as one variable. And so to do that, let's solve this first equation up here at the top for y. So let's subtract 2x on both sides. There should be 2x. And then to solve for y, we're going to take this equation up here and then divide by 2. So if we divide by 2, y is equal to 50 minus x. Okay, now what we're going to do is plug this in here for y. So now we have one equation with one variable, and that's going to be the key to solving this question. So instead of writing the area is equal to x times y, the area is equal to x times 50 minus x. Because 50 minus x is defined as y. Okay, now this equation is an equation that represents the area in terms of one variable x, and this is what we're going to optimize. So before we take the derivative, let's distribute the x to both terms. So a is equal to 50x minus x squared. Now let's take the derivative of this equation. So x prime, well, the derivative of 50x is going to be 50 minus the derivative of x squared, that's 2x, and we set that equal to 0. So now let's solve this for x. Move the 2x over and now divide by 2. So x is equal to 25. But we want to make sure that we're maximizing the area, so we want to make sure that this critical point here, x equals 25, is a relative maximum and not a relative minimum. There's a couple different ways we can approach this. The easiest way to do it in this case is we're actually going to find the second derivative. In this case, so the second derivative in this case is negative 2. And that tells us that the second derivative at this x value is negative, which means that the function is concave down, which indicates that the shape is going to look something like this. So because it's concave down, there's a maximum here. So x equals 25 maximizes the area of the function. Okay, and we can prove that using the sign of the second derivative. Now to actually solve the dimensions, we need to take the x value and then solve for y. So we need the y value as well. And to do that, we're just going to go back to the perimeter equation from the top. So to solve for y, we're going to use this equation right here. So we know that 2 times 25, our x value, plus 2y is equal to 100. Now let's solve this for y. So 50 plus 2y equals 100. 2y equals 50. So y equals 25. So the dimensions then in this case, our answer is going to be 25 meters by 25 meters. So among the rectangles with a fixed perimeter, a square is what maximizes the area. Okay, let's do a practice question. This one's going to be calculator active. So we're going to find the maximum area of a rectangle that has 2 vertices on the x-axis and 2 vertices on the graph y equals x squared minus 8. Okay, so what does this look like? Let's say we have a coordinate plane here. And we're going to have the equation y equals x squared minus 8 going through the coordinate plane. X is over here. Okay, and the way this looks, well, the way this will look is we have 2 vertices on the x-axis, and then the other 2 vertices are here, somewhere on the function. Okay, and our goal is to figure out the maximum possible area we can have within this region. So let's go through a couple of just coordinate points before we do this. Well, first of all, we are bounded by the following coordinate points. The x-intercepts here are going to be plus or minus root 8. And so the x values that we're going to be talking about are kind of bounded below and above by negative and positive root 8. These coordinate points here we're going to call negative x, because we don't know what the x value is. We're going to solve for this x value, and this will be positive x, comma 0. All right, and then lastly, this is 0, comma negative 8. Okay, so the area of this rectangle. This right here, sorry, is x squared minus 8. The area of this rectangle is equal to the base times the height. Well, the base is going to be this first distance here. And that's going to be, if we're doing the distance from negative x to 0 and then the distance from 0 to x, the base is going to be 2x. All right, and then the height is this value here. This one is a little bit trickier because the height is defined as the value of this function. But if we plug in a x value here, it's going to give us a negative value for our height. We cannot have a negative as the length, because the length of something can't be negative. So what we're going to do is we're actually going to change the height so it is negative times negative x squared minus 8. So again, because the height, because the y value is going to be a negative value, we have to change that value to a positive, because when we're talking about the height of this rectangle, we're talking about this length right here, this length. So we have to change the sign. Now let's rewrite this. Okay, and now we have one equation with one variable, which we can then use to optimize this for x, which will give us our area. So here's a in terms of x. Let's take the derivative of this and set it equal to 0. Before we do that, let's actually just distribute. It'll be easier so we don't have to use the product rule. So we have negative 2x cubed plus 16x. All right, and then we're going to take the derivative of this equation. So negative 6x squared plus 16 equals 0. Now let's solve this for x. So we can move the plus x squared on both sides. So we end up with the following. Divide by 6. Well, this is the same thing as x squared is equal to, if we divide by 2, 8 over 3. And so x is equal to plus or minus root 8 over 3. Well, if we're talking about x, x is going to represent a length. And so we're only going to deal with the positive. So x will be positive because it's a length. So this has to be the positive value. So what we can do is make the sign chart. Let's prove that it's a maximum using a sign chart instead. You can do the second derivative or you can do sign chart. Well, the derivative is bounded. The x values are going to be bounded by 0. And then if we go back up to our graph here, the maximum possible x value we can have for this figure to be in the region we want it to be is root 8. And so we're going to have root 8 over here. And here's our critical point, root 8 over 3. Okay, and if we take a value that is between 0 and root 8 over 3, let's take like a very small fraction, like let's say positive 1/4. That is going to give us a positive value here if we plug it into the derivative. So this right here is positive, and then this will be negative. So because the derivative, a prime, goes from a positive value to a negative value across the critical point, that critical point represents a maximum. And so the b value, the base, we defined as 2x, and so the b value is 2 times square root of 8 over 3. The h value represents the height, which we can find by plugging this function into the equation of the function, x squared minus 8. So, but it's negative, so it's negative root 8 over 3 squared minus 8. All right, if you simplify that, that becomes 16 over 3. And so the maximum area here is going to be the base times the height, which is 2 root 8 over 3 times 16 over 3. Okay, and let's just plug this in our calculator and see what we get. So 2 times the square root of 8 divided by 3. And then we're going to multiply this whole thing by 16 divided by 3. And so we get 17.418. Let's round it up to 17.419. So that's going to be the maximum possible area. 17.419. I'll draw it in purple. All right, we're going to finish this video by going through one more. So one more that I think will probably be, hopefully, relatively similar to this one we just went through. Another one dealing with like a rectangle on a graph. So problem set number 1. Let's say we have a rectangle that has, it is defined as this area between or under the function y equals 4 minus e squared, where we'll call this some x value, the distance from the origin to this point, and the y value is the height here. All right, we want to figure out the maximum area of this rectangle, and this will be calculator active. So the first thing we're going to do is we're going to come up with an equation that represents the area of the rectangle in terms of one variable, x. Okay, so the x value, let's actually just draw the coordinate points here. This first coordinate point is 0, 3. If we plug in 0 into the function, we get 3. This one's a little bit trickier, but it's the natural log of 4, 0. That is what you get when you set the function equal to 0. So that just tells you kind of how the x values and the y values are bounded. So a is equal to x times y. So the a value in this case is equal to x times 4 minus e to the x, because that's what y is equal to. Okay, now let's take the derivative of this. To take the derivative of this, you can distribute this, but I think it's actually easier if we keep it as is, because we're going to go straight to the product rule. And that is when we take the derivative of the product of two functions. It is the first function, the derivative of the first function times the second function, plus the first function times the derivative of the second function. So if we apply the product rule to this equation, we end up with 4 minus e to the x, because the derivative of this x here is 1, plus x times the derivative of 4 minus e to the x. Well, that will get you minus e to the x. Now let's rewrite this. 4 minus e to the x minus x e to the x. And we're going to set the derivative equal to 0. Okay, so the question is, where does a prime go from, if we want to maximize this, positive to negative? Okay, and we're going to use our calculators for this. So where does the derivative, this function here, go from positive to negative? So let's take this, and I'm going to plug it in for y equals into my calculator. So 4 minus e to the x minus x e to the x. Okay, and let's change the window to our bounds that we talked about before. The maximum x value we said was natural log of 4, and then the y values, let's just do negative 5 to 5, just so we get an idea of what the graphs will look like. So where does the function go from a positive value to a negative value? Well, it's going to be, I don't know if I can write on this, right here. And so to do that, to calculate that, we're going to go to second, trace, and go down to the 0. Hit left bound, go to the right. Hit right bound, go to the left. And approximate where we think it might be. And so we get an x value of 0.799. Okay, so the x value here, that gives us the location where the derivative goes from positive to negative is 0.799, which means the y value is 4 minus e to the 0.799. Okay, let's plug that in just real quick. 4 minus e to the 0.799. So we get 1.77, let's round it up to 1.777. Okay, we're almost done. And so the final answer is going to be the product of the x value and the y value. So 0.799 times 1.777, 0.799 times 1.777. Okay, and 1.419, let's round this up to 1.420. That's going to be the maximum possible area for this function, for the rectangle underneath the function. Okay, so the main idea is we take the derivative represented in terms of one variable, and then we take that derivative, it's set equal to 0, and then solve for x. Okay, if you're finished with this video, let's move on to problem set number 2, where you're going to work through the following 3 optimization questions, and the key is below, and this is located on the OneNote.